So first, we're going to talk about what's called acceleration as a terms of change in velocity. And you've heard this term before, so I don't need to wow you with an experiment, but we're going to do something very simple to discuss acceleration. So when you're in the car and your folks say step on the gas, or somebody says step on the accelerator, it's called the accelerator because what does it do? Yeah, it makes the car move faster. It changes your velocity. Perfect. It changes your velocity. And then we're going to talk about graphical representation of this. So as we saw the graphs with position versus time, now we're going to see graphs with velocity versus time. And when the velocity is changing or growing, it means it's accelerating. Or when the velocity is going down, it means it's decelerating. So we're going to see these terms. And then we're going to talk about our kinematic equations, which are really one of the most important things we're going to learn this year. Okay, so this is an extremely important topic. It's going to be used in other sections after this. Okay, which happens a lot with physics. You're going to see the cumulative nature. So let's start first. We have our definition here. All I want to do is talk about acceleration, and the easy way to prove acceleration is by a simple experiment. So I'm going to start with this ball. I'm going to release it off the track. We're going to hope that it stays on the track perfectly. Okay. So what we're going to do is we're going to time the actual distance that the ball covers in 1 second, in 2 seconds, in 3 seconds, etc. So I need one person to just come up with a stopwatch. So you have your phone with you by any chance?
Yes.
So a stopwatch. And Ryan, you want to come up and show your hand? You can be the person dropping this. So all Ryan's going to do is release the ball from the top. Ernest is going to start the stopwatch. Now here's going to be the tough part. It's not easy to do this, so you guys have to figure out a way to make it work. What you want to do, Ernest, is after a certain amount of time, tell him to stop the ball. Okay, so you have to figure out what the good times will be to use. So maybe after a second, after 2 seconds. So when you get to 2 seconds, you might have to say stop, and he stops it and marks off where it is. Then he's going to do it again, the same way, and he's going to mark it off at a later time. So now, Ernest, you're going to pick maybe 5 seconds as the time to use. But I would recommend going by increments. So 2, 4, 6, or 3, 6, 9, okay? And what you have to do is listen for him. So you're going to release it. Actually, Matej, come up, be the third person. And when he says stop, Matej's going to actually stop it. So you're going to start it, and he's going to stop it. Simple enough? Now, you can do this in a much more complex manner with what are called photo gates. You put a little gate here and a gate here, and there's a laser. And the laser on the first one connects to one of the sensors. The second one connects to the sensor. When it breaks the first sensor, it starts. And when it breaks the second sensor, it stops. So if you want to think more precisely about an experiment like this, you can do it. But this is just a simple way to start, just to show you guys the idea. So you guys figure it out. Okay?
So I'm going to say 3.
And if it doesn't work, you can change. Try another one.
Alright, start. Stop.
So that was 3 seconds, right? So what's going to happen, obviously? If you're going to go longer, is it going to be able to stay on the ramp? Did it cover more than half the ramp? Covered probably at least half the ramp, right? Where are you at? Right there? So we're 140 out of 277. So it covered about half the ramp. So it's probably going to go off the ramp, or is it going to get faster or slower? It gets faster because it's going downhill, right? So it's going to probably go off the ramp, so maybe 2 seconds. So you got to be you got to get ready for 2 seconds. Now, one thing we could do, if you'd like to, it's easier to stay in the track on this side, I think, than this side. But we don't have the marker. So what we could do, though, is go this way for now and just look underneath to get the marking afterward. Would you agree with that? That'd probably keep it on track better? Because when you did it the first time, what happened, right? It kind of went like that. So it delays the motion. This should hopefully keep it in track. It has grooves here. So maybe let's try setting it right in the middle groove. And now here's the thing. Make sure for the second time you have the exact same startup. So make sure it's the exact same point.
Start. Stop.
So take a look underneath, so keep this marking. Where are we at?
87.
87? All right, so 2 seconds. Let's keep data. I'll put data on the board here. Good. Go ahead.
Start. Stop.
Centimeters, right? Yeah, it's got to be.
No, ours is really 40.
What was that one just now?
You did 2 again.
You did 2 again? You got around 90? That's fine. No, we'll do a few trials at 90. That's a good idea. Do one more trial. Do one more trial for 2 seconds, and then we'll go to 4 seconds. Yeah, we should collect a little bit data so we at least have some reasonable,
Start.
values.
Stop.
Ooh, 77? Go one more. If it was like 89, I'd be like, all right, like it looks like we're at the same ballpark, but that bothers me a little bit.
Start. Stop. Ooh, that was long. That was long.
106? So what can we say about the validity of this right now? It's looking pretty fishy, right?
Yeah.
Try one more. Then this is why if you were doing this for a real collection of data, what would you use? You'd use a photo gate, because it literally uses a laser and responds at the speed of light. As soon as it touches, it responds.
All right. Start. Stop. I think that's better. Hopefully.
All right. Let's go to 4 seconds.
4 seconds, okay. Start. Stop.
178.
Start. Stop. Ooh.
I mean, theoretically, when you think about it, since it's picking up speed, it should cover more than twice the distance and twice the time. So numbers around 200 are probably more reasonable than even 178. But keep going. Don't finagle the data, but just understand the data.
Start. Stop. Whoa.
Try again. Ernest, come on. Ernest, my man. Jeez.
All right. Start. Stop.
Okay. 2 more.
Start. Stop.
Right at the end.
At the very end.
227.
You're gonna change. It's the last one.
Stop.
That was the last one. What? All right. Why would you guys change readers on the last one? You at least had consistent person reading, and then you changed on the last data point. You just picked a different person.
Because I feel like I kept messing with it.
No, you didn't mess it up. All right. Let's talk first for a second about it. Before we even begin to analyze the data, let's talk about issues with collecting data clearly. What were some of the things that could have caused problems? Give me some examples. Okay, never answer with human error. Give me the human error, please. What human error are you talking about? Sure. It's again, there's delay in the human cognitive response. Agreed, that's one. But we don't say human error.
Stopping the ball, like when it says stop.
Yeah, when he says stop, the time it takes to actually stop it, and doesn't always stop perfectly. It's not easy to stop it. You noticed after a little while. What else? There's more. Come on, there's more to it than that.
The way I let it go, sometimes it could have accidentally pushed it a little bit.
So yeah, Ryan's exactly right. Look, he might have been pushing down one time, and then maybe when he let go, he gave it a little nudge. Or other times, maybe he it stuck to his finger a little bit. So what would have been the easy way would have been put a little gate right here, and then just release the gate, so there's no actual person involved in it at all. Maybe you just pull on the string and it pulls the gate back. What else? You could have seen it better over here. This area. What else?
But stopped it. Same thing like the gate almost.
If we had a gate to stop it for, I agree. But there's something else I'm thinking of that's different than the gate.
Maybe if it touches the ball.
Yeah, didn't you guys see it over here? I saw it. That's why I was standing there. It was doing this sometimes. See how it's going from side to side? It was kind of bumping back and forth because this is not a perfect track. This side was better than this one, though, for an object like this, right? Normally, what I would do, and I could do, but I should have actually had you get them. There are little carts up there. And I could just start with the cart, and the cart could sit on the grooves and maybe go a little bit better. So what I'm going to do for the second class, instead of using this object, maybe I'll take some of those carts down and try to see if the wheels are broken on those. They're old. So if one or two of them are good, or I could fix them later, I might try a cart, because the cart would go down smoothly, right? There'd be a lot less room for loss of energy. And later in the year, you're going to learn about this. See the bumpiness along the way? Do you see all that happening? That's losing energy at all times. So when it's losing energy along the way, it's not picking up as much speed as it should. So honestly, I got a little bit nervous because I'm looking at this number, 178. And 178 is definitely way too low when you compare it to the numbers up here. What's the average for the 2 seconds? Anybody get an average for me? Give me an average for both. Okay? For the displacement after 2 seconds and after 4 seconds, give me an average.
centimeters for 2 seconds.
89. Gotta be quicker, come on, man. And the other one?
Oh, that's a perfect.
207.
Another 205.
You got 205, you got 207, so let's get another. Somebody else verify. What do you get for the second one, the average? That's why you're supposed to have calculators. So many people on that test, by the way. Man, talk about waste of time. Doing all the math and the margin. Killing me. 207, I got 207 twice. Oh, all right. Well, I mean, it might be right in your head. I don't know. Anyway, let's take a look at this.
Oh, wow.
If acceleration didn't exist, what would happen? All right, really good theoretical answer. I like that. But in this kind of experiment, say I gave it a nudge, right, with a certain velocity, and acceleration didn't exist. What would I notice about my answers?
The 4 seconds would just be double the 2 seconds.
Exactly. If I gave it a little push to start, right, and there was no such thing as acceleration, so I give it a little velocity, it would maintain that velocity forever. If it maintained that velocity forever because there was no acceleration, then the answer should just be double. That's really what you should see here. Again, if there was an acceleration, this answer should simply double if you gave it a little nudge. Obviously, it was a different experiment. We didn't even give it a nudge, but theoretically, again, it should not be more than double if acceleration didn't exist. So we can see here that it covers only a certain amount of ground, and then it covers more than that in the next 2 seconds, which means that the velocity is just getting larger. What's the average velocity in the first 2 seconds? You just divide this number by 2. So the average velocity is going to be 44.5 centimeters per second. That's how we can find the average velocity, right? Displacement over time. In the second 2 seconds, you would take this minus this, get your gap there. That's going to be what, 111 plus 7, 118 over 2 seconds again. So that one's going to be instead 109. No, never 109. That's going to be 118 divided by 2 is going to be 59 here. So we got 44.5 centimeters per second and 59 centimeters per second as the average velocity. So what happened there? Your velocity went up by almost 25%. Almost 25% there. And the reason for that is because of acceleration. Why did this accelerate down the ramp? What's causing it to accelerate? Gravity. That's really how we understand gravity. With falling objects, it's a lot easier to see. You actually see the gravitational constant. Now, we're going to do a real experiment of this in our double period when we have a lab, a little bit more intricate than this, with photo gates, with what are called picket fences, and it measures motion vertically. And it's amazing the data you're going to get, and your group did this last year. It's so precise. The acceleration of gravity on Earth is 9.81. We were getting answers as close to like 9.805. Really precise data from it. Because again, this was experimental with humans involved. That's going to be a sensor, and the sensor is going to detect when the object passes through the laser and the exact distance each time and give you the acceleration. Okay, and we're going to see how that comes out with graphs as well. So let's continue with this. Thanks. So let's continue with this now. So the definition we're seeing here for acceleration, just in case you want to formally understand it, is the rate at which the velocity changes. So it's a simple equation to remember, but you don't even have to memorize it. Okay, you don't have to memorize it. You have the change in velocity over a time period. This is analogous to the last formula. What was the last formula? What was the last formula? Who remembers? Last chapter, what was the formula we used? V equals x over t. It's analogous. I mean, look at this. X was really the change in displacement over a time period, and that gave us velocity. Well, now we look at the change in velocity over a time period, and that gives us acceleration. So the idea here is it's not a coincidence that these formulas look similar. If you go on to take calculus, you're going to learn that this is something called a derivative. It's a motion within a motion. It's a motion of motion. It's a change of motion that's occurring. And you're going to see that there's going to be a graph for this that's going to be very similar to the graphs we looked at in the previous section. But instead of it being, remember in the previous section, the graph was x and t, right? Remember that? Look at the formula. The formula is x over t. The graph is x and t. So what do you think the graph is going to look like for this one? Say again? Not t over x. Again, take a look. The formula x over t referred to this graph, and we got velocity from the slope. Remember that? Lauren?
So the other graph would be t over t?
Will be what?
Would it be v?
V versus t. Very good. V versus t. That's the graphs we're going to look at this chapter. And we're going to see the slope of that. And the slope of that is going to give us acceleration now. Remember last time the slope of this was just change in y over change in x, or change in the vertical component over the change in the horizontal. Well, it's the same thing here. The vertical component is velocity. Change in that versus change in time is going to give us acceleration. So we're going to see in a little while that the slope of this will give us acceleration. We're also going to see it in the lab with the picket fence, and then we're going to see it in the second half of the lab that we started the other day. Okay, so this is where this comes from, this term acceleration. Units are very important to understand. Meters per second over second, we went over this earlier in the year, is meters per second squared. That's going to be the unit for any acceleration. Okay, length over time squared. So kilometers per hour squared, that's an acceleration. Feet per second squared, that's an acceleration. Okay, any sort of length over time unit squared. So let's look at this first example. A shuttle bus slows down with an average acceleration of negative 1.8 meters per second squared. Why is it negative? Why is it negative? It's slowing down, good. And also because it just means it's going to the right and slowing down. Think about it for a second. If I'm going this way and there's a negative or opposing force against me, wouldn't it slow me down? You're going to learn later in the year about Newton's laws, F equals ma. Well, the forces would cause that negative acceleration. So I'm going this way, and the wind is blowing against me, slowing me down. Or I'm driving my car and I'm hitting the brakes apply an opposing force where they slow down your tires. Theoretically opposing. How long does it take for the bus to slow down from 9 meters per second to a complete stop? List your givens. List your givens. And now keep in mind that you have more than one velocity to write down. So you might want to specify with a subscript. What's one of your givens here? Okay?
So your acceleration, 1.8.
Specifically, not.
Negative 1.8.
Thank you.
Seconds.
What else? Ernest?
It says, how long does it take to go from 9 meters per second to complete stop?
So that's,
Time.
okay, so that's what we're looking for. Good.
Time and distance. How long when is it complete stop?
We don't, what does that mean? What is a complete stop? What information do you know about an object when it's stopped?
No velocity.
Yeah, so the final velocity would be 0, we could say.
Starting is max.
Yeah, the starting or initial velocity is 9. Very good, guys. Good breakdown. But this is what I mean. So when you're doing those math problems on the test, I saw a few of you with highlighters on the test. That's new to me. I've never seen that or done that. That's okay, I don't mind. But this is the information you should be highlighting, right? So if I'm highlighting this, let me change my color of my highlighter. Let's see if I can make this. I don't know how this works. All right, let's see if this works well. I'd be highlighting this. And then I'd be highlighting this. And then this. And then maybe even this. How long? Those are the things we have. Acceleration is negative 1.8. That's highlighted. How long? That means time. 9 meters per second. That's initial velocity. Complete stop. That's final velocity. See what I'm saying? So those are the portions I would highlight and then write down. Jake.
5 seconds.
I don't know. Would it be 5 seconds? Is that what we get? Did anybody check? Let's see. What formula should I use? What formula? Again, I'm going to make believe, Jake, that I don't know, okay? So let's say what formula would we use, because that's really the approach. You have two formulas to choose from. V equals x over t. Or A equals change in V over t. Which one are you going to use? Which one, Lauren? I think it would be that one. Because if I use this formula here, whoops, I need the pen. If I use this formula instead, I don't have x and I don't have t. So can I physically use that formula? Because I have two variables missing. You can't have two variables missing and only use one formula. It's not possible. So this formula is no good because x and t are unknown. So don't use this. And then look to the other formulas available. You're going to see there's going to be 5 formulas actually available by the end of this lesson. So as of right now, though, there's only 2. So you're still kind of like, all right, no big deal. We're using this one. And you don't need the delta for t if you don't want it, because we always know it's a change in time. Okay, it's a time period. The delta for the v, though, is important, because delta means final minus initial. Final minus initial. Delta is change. Delta means change. Final minus initial. So this formula here becomes this. Again, the way this formula is given on your formula sheet is this way. This is how you're going to see it on the formula sheet. You need to know that delta means change. Final minus initial. For the rest of the year, delta will always be final minus initial. You will never do initial minus final. You need to be consistent with your work. We will always do final minus initial. Is that clear? Because it's going to come up a lot. You're going to see the term delta a lot. All right? So at this point, what are we trying to solve for? What's our goal variable? What are we looking for? Ernest told us what it was earlier. Maya, finish it. T. We're trying to find T right here. So if I want to find T, it's in the denominator. What can I do, though? That trick I keep telling you.
Just switch it.
With A. Switch A and T, and you've got T by itself now. Let's take a look. Oops, this is A. I'm sorry. Let me make the correct variable there. It's not a coincidence that the acceleration was negative. Now it makes sense. Because what kind of an answer can time only be? Time can only be positive as a real answer. And we'll talk about negative time when we get to chapter 4. And I'll explain where that kind of makes sense. But here, we're going forward in time. Time can only be positive. Well, look, I've got final velocity. Well, that's 0. Minus initial velocity over the acceleration. So it's going to be negative 9 over negative 1.8. Negative 9 over negative 1.8, which is simply, as Jake said, 5. What are my units for time? Seconds. If you forgot the answer was in seconds, just look at your units. Meters cancel with meters. Take a look, I'll show you here. The meters up top cancel with this meter. Seconds down below cancels with one of these seconds. So I've got seconds left. It's in the denominator of the denominator, which means those units bump up to the numerator. Okay, I spoke about this the other day also. The units in the denominator of the denominator end up in the numerator, which is where seconds come from here. But again, you could remember that if you're in meters per second and meters per second squared, your answer for time's got to be in seconds. It's not going to be in minutes. It's not going to be in hours because you started with everything in seconds in the beginning. The concept of VI and VF is going to continue for the rest of the year for a lot of things, not just V, but anything, initial and final. Whenever you're going to use initial and final, it means that you have 2 scenarios. You have like a before and an after. The before is the initial, the after is the final. You could break up any problem into pieces. For example, let me give you a simple way to visualize this, because students struggle with this throughout the entire year. Let's make believe that this roll of tape is launched from this tape from the desktop. It's thrown and it continues to roll across the room. Now, it goes all the way to there, and it's going to stop eventually once it hits an object that causes it to stop. Maybe it'll roll all the way to your guys' feet. The concept of it, though, is that you can break this problem down into before, being the velocity when it's launched. You can make the final right when it's about to hit the ground, and that's the end of the problem. And later in the year, you're going to see how we're going to talk about energy, where it's before, meaning the height it starts at, and after when it's about to hit the ground. So I could call that final. Or I could call the end of the problem final over there, where it ends up. Or maybe I call this initial, this final, and then I start like a new problem. And I use the data from this part, and now I call that initial, and I call that final. And I break the problem into pieces. The mathematical word, which you don't have to know, is called truncating. And you guys, I think, saw this, or you will see that this year at some point when you look at piecewise functions. A function that behaves maybe as a linear function, and then becomes parabolic, and then it becomes maybe in this case like a log function, and it teeters off. So different pieces of the function behave differently. In these problems, you're going to see throughout the year that you might have to break a problem into 3 parts. There might be a before and an after, an initial and a final. You might have to say, okay, you know what? I have 3 parts to this problem. The result of the first part is the beginning of the second part. The ending of the second part is the beginning of the third part. You see what I'm saying? So let's say you calculated the velocity for some reason in the problem, and you determine that so you start here, the velocity here is 10 meters per second. And then something else happens to the object. Well, now it's like a new starting velocity of 10 going into the second part. And let's say the second part causes it to slow down for some reason. And you slow down to 3 meters per second. Well, now 3 meters per second is the beginning of the third part. So your ending could be the beginning to the next portion. So this problem, it was relatively easy because there was just a beginning and an end. You start at 9, you end at 0. But soon we're going to see that there are a lot of problems that involve several portions to them, and you have to be able to break down a problem into different pieces. It's going to get easier because we're going to practice more, but the concept is going to continue throughout the year, whether it be velocity or energy or different types of problems. So let's quickly look at this concept of a graph, and we saw this already. So this is something you've seen in your first section. You also saw this in your summer packet. And I had you take a look at a curve that had velocity versus time on the curve. Now, if you remember, when I gave this to you as an example in your summer packet, it was a linear function. It was a function that looked something like this instead. Right? It was v versus t like that. That blue one you see on the right. Well, this is no longer a linear function, but we could think of this in pieces again, in pieces. So from the beginning here, let's think of this from the beginning all the way to part A. From the beginning to part A. Could you approximate that? Could you approximately say it's almost linear in that portion? Probably. It's relatively linear. Look at the beginning here. This is almost perfectly linear, and then it starts to curve a little bit before A. So we see, I should point with the cursor so you can see this later. So we're going to see here that, again, this portion is really pretty much linear up until here. And then it starts to curve right there. So we can see that this is kind of a linear function. Well, if I were to look at this, I could determine the slope in that range by taking, again, y2 minus y1 over x2 minus x1. If I give these values, what values would they have? I'm asking for numbers, but what would their units be in this case? What would the coordinates be? They would both be positive, for sure. Very good. Both time and velocity will be positive. Give me sample numbers. Obviously, this is 0, 0 here. It's the origin. Give me another number, and what would the units be based on the axis labels?
It would be like 5.
5 what? What are the units?
2.
What are the units? Dimensions, units. Time. What are the units of time?
2 seconds.
Seconds, that works. So you said 5 at first, I put 5. 5 seconds. All right, so 5 seconds later, what might the velocity be? Pick a velocity, but give me the units. Tell me what units for velocity are. Doesn't matter what the number is. You can't be wrong. All you have to answer is with units. Ernst?
2 meters.
2 meters? Are meters lengths? What's velocity? What's velocity? Meters per second. Okay, I'm asking this because I felt like on the first test and the first problem set and looking at your homeworks, a lot of you are forgetting units in different parts. When you practice, if you practice incorrectly in sports, do you play well in the game? Honestly, athletes in the room, no, right? I mean, if you practice the wrong way, if I teach you how to swing a bat with this arm and it turns out, or this is a lead arm, turns out you're a righty. Is that going to make any sense? No. You wouldn't practice to throw your left hand if you're a righty. Well, practice your work correctly. A lot of you are not including units in different spots. Okay, I'm mentioning this right now because of the fact that I saw this as a repeated thing on the first test. Many people lost half a point for getting units. Now, why am I bugging you about units right now? Here's the reason I'm bugging you about units. Look at the slope. Figure out the slope of this. If I wanted the slope between these 2 points, I would find the change in y over the change in x. All right, so it looks like for y, I've got 2 meters per second minus 0 meters per second. That's the y value. Again, how do I know that? I look here, 2 meters per second and 0 meters per second. The x value is going to be 5 seconds minus 0 seconds. Therefore, as a result, my slope, in this case, m, will be 2/5. But what are the units of that slope? And this is something that you saw in your summer packet. And some of you answered this correctly already at one other time. What would the units be? The number is 2/5 or 0.4. What would the units of that be? Lauren? Close, Lauren. I get why you're thinking maybe just seconds, but it's not just seconds here. It's not just seconds here. Somebody help her out. Maybe look at your units. Try to look at the dimensions you have. What are the numerators units, everybody? What are the numerators units? No, the whole numerator here. Meters per second. What is the whole denominator? So it's meter per second per second. Meters per second squared. You saw that yesterday or last week in your last lesson. Meters per second squared. What does that represent? Acceleration. Acceleration. I'll go into where the meters per second squared comes from. Yeah, Ernest, go ahead.
I was just asking, how come for this one cube normally just cancel out the seconds since it's...
You wouldn't because look, see where are the seconds in the numerator? Aren't they in the denominator of the numerator?
Yeah.
Aren't these in the numerator of the denominator? They need to both be in denominators or both be in numerators. So if this meter and this were meter, you could cancel them, right? Because they'd both be in numerators of their positions. But this is in the denominator, and I'll prove it to you. If I take meters per second and divide it by second, meters per second divided by second. That's how I always do this to prove. Then you say, okay, well, division means multiplication by. So you get meters per second squared. Those would be my units. Okay, this is on the bottom here is all units I'm showing you. So what I want you to get at is this, and write this down in big, bold letters, please. The slope of this is velocity versus time now. This is a different kind of graph than we did in the last chapter. And you guys are lucky, by the way. Last year, I had both these types of graphs on the same test. And students got so confused because position versus time, velocity versus time, they were confused about that. But here, the slope of a velocity versus time graph is acceleration. The slope of a velocity versus time graph is acceleration. The slope is acceleration. And think about it logically. Somebody helped me with this at one point. I forget, it was the other class I actually asked this. Maybe I'll ask it here. Go ahead, ask your question. Yeah. What do we notice is happening physically from here to here? What could you tell me about the behavior of the object? From the origin to A, what is happening, Lauren? It's positive slope, good. What else?
It's moving away from the sensor target.
Well, again, this is not position, so you can't tell me about moving away necessarily unless you really know more, which you could, but this is not a sensor anymore. So we're not looking at this as position anymore. Acceleration is not increasing.
I said the speed is increasing.
The speed or the velocity is increasing. Different things. Again, right now, look at the actual graph. The y-axis is velocity. So by the velocity in the graph going up, you know that the velocity is increasing. What happens to the velocity at point B? Be careful with your answer. What happens?
Is that it's the slowest point?
I wouldn't say it's the slowest point. I wouldn't use that word.
Well, I'd say like it almost stops.
Again, you guys are interpreting this as a position graph. In a position graph where it's flat, it stops, right? But if the velocity is the same for a while, what could you say?
It's going at a steady pace.
It's moving at a steady pace. Be careful. This is where it's going to get wild because you're thinking of position, right, from last chapter? So watch what happens. And I'm going to dictate. If you want to, you could write this down if it helps. Velocity is increasing. Velocity is increasing. Velocity is increasing. It's still increasing, but it's not increasing at the same rate. Now, ready? Velocity is constant. Velocity is constant. Velocity is constant. Velocity is constant. Then velocity is decreasing, velocity is decreasing, velocity is decreasing all the way until the end. So velocity is increasing. So in this region, here's what you want to write down. You have positive acceleration. Positive acceleration because velocity is increasing in this region from 0 to A. How about in this region at B? What could I say? I want two statements again. Here, I was saying velocity was increasing, so you have a positive acceleration. What statements can I make in this region? What statements in this region, Matei?
Well, would the slope be undefined, so...
Not undefined.
0.
0. Remember, undefined is a vertical line. The slope is 0. You're on the right track. Amaya? The velocity is constant, so the acceleration or slope is 0. Again, velocity was increasing, so positive acceleration. Velocity is constant. Velocity is constant, so 0 acceleration. Then what happens? What happens when your velocity decreases? What must you be doing in the car? To slow down in a car, what must you be doing?
Slowing down.
What do you physically have to hit?
The brakes.
The brakes. The brake is a decelerator. So this is negative acceleration because the slope is... I'm leading you toward it. The slope in this range is negative. Again, slope is positive, positive acceleration. Slope is 0, 0 acceleration. Slope is negative, negative acceleration, also known as deceleration, meaning it's slowing down. Please remember, circle it if you have to right now. It'll get easier because we're going to look at more of these, and the lab we're going to do is going to have this also, both labs. This is not position versus time. A few of you answered the question in the beginning, thinking back to the old graphs. This is not position versus time. So if you need to circle something or highlight something, highlight the word velocity and write yourself a note. This is a graph of an object's velocity, not its position. This has nothing to do with a motion detector in motion there. It's not like it's moving away and then it's staying still and then moving back to the detector. That is not happening. This simply means velocity is increasing, velocity is steady, velocity is decreasing. That's all that's happening here. Okay, that's all that's happening here. All right, I'm going to go on to the next part. If you're a tiny bit confused still, it's not a big deal. If you're really confused still, maybe at some point before we go on to the next few days, you come by and we'll go over this together, you and I. Okay, so we're going to take a look now at this concept in a more tabular form, in a table. Okay, so I'm going to help you guys to understand this a bit. So let's think for a second. We're going to talk about initial velocity and acceleration. We're going to talk about initial velocity and acceleration, and we're going to put in values here that correlate to these actual motions. So tell me, when you're driving a car, all right, let's say you're driving a car in the positive direction. Positive direction, not the negative direction. Remember, positive and negative matter in this class. So I'm saying to the right for you guys is positive. You're driving your car in the positive direction. What's the only way you can speed up? What's the only way you can speed up? Hitting the acceleration. So accelerating which way? Positive. Would you all agree? Okay. So if I'm going in the positive direction, by having a positive acceleration, I will indeed speed up. I absolutely agree with you. It makes sense logically. Just use logic right now. Use common sense. If I'm moving this way and a gust of wind pushes me forward, doesn't it make me go faster? If I'm going this way and I slam on the gas, I'm going to go faster. So positive velocity and positive acceleration means I speed up. What if instead of driving this way in the city, now I'm driving in the negative direction, but I still want to speed up in that direction? So I'm driving negative. What kind of acceleration do I have to continue to go faster? Does the acceleration have to be pointing this way or pointing this way? If I want to go faster, this way. It's got to go this way. It's the only way. Again, I'm walking down the hall and somebody kicks me in the back. It's going to push me forward, right? It's accelerating me forward, but in which direction in this case? The negative direction. But in this case, look, I'm looking at the speed. I'm still speeding up. But in which direction? In the negative direction. So if you're moving with negative velocity, and you have more acceleration in that direction, you're still speeding up. And this might confuse you for a moment because you're saying, how could you have negative velocity and negative acceleration and get faster? You're just getting faster, but in which direction? To the left, or in the negative direction. So in both of these scenarios, you are speeding up. Now, and it'll come to be a bit more clear once we get to the second one. When can you be slowing down? When can you be slowing down? Lauren?
When you're going in a positive direction, but at like a negative velocity, or not velocity, like
Close, but with a negative
oh, sorry.
acceleration. So let's go through that. Positive, negative. She's absolutely right. And let's go through this. Ready? I'm driving my car to the right. I know it's kind of ridiculous to say to the right, but in the positive direction. And how do I stop or slow down? I hit the brakes. When I hit the brakes, it applies a negative acceleration. A negative acceleration. It's like the wind. You're running in the park, and instead of the wind being behind you, now the wind is in your face. And you're trying to run through the wind. Okay? You would feel that pushing against you. How many of you have skied or snowboarded before? If you have, you know that feeling when you're rushing down the mountain and the air is rushing off your body. It's actually slowing you down. So what do you see skiers? What do they wear? Like real skiers, like professional skiers. What do they wear?
Tight.
They wear like skin-tight outfits. Why?
More.
To reduce the... What's the word in physics that you're feeling that's slowing you down? What's it called again?
Friction?
Friction or drag, either one. Air resistance, drag, friction, any of those work. So they reduce the friction or they reduce the negative acceleration. Well, again, the only way to slow down is to have opposing signs there. So what if I'm going this way? If I'm going with negative velocity and I want to slow down, which way do you have to push me? Yeah, you got to push me positively. Again, you're a linebacker in football. And the running back, anybody watching any games yesterday? Some good games. Some terrible, if you're a Jets fan like me, terrible games, obviously. But I did win fantasy, so I'm all right. Yeah, screw all of you guys. So, yeah, if you're a Jets fan, it was a terrible game. So, you're running this way, right? You're the running back. The only way a linebacker can tackle you is by pushing against you. So, if you're running with negative velocity, he or she has to push you with positive acceleration. So, again, opposing signs. So in both scenarios, if you're moving one way, the only way to slow down is with the opposite type of acceleration. So write yourself little notes on the side. Look, right here in the margin. When the signs are opposite, you're slowing down. When the signs are the same, you're speeding up. That's the conclusion you make in your margin. Those are the little asterisks you make so that when you take multiple choice on the next test, you get them like that. Because these are the questions that are asked in multiple choice. The velocity is positive and the acceleration is negative. Discuss what's happening to the object's motion. Okay, the velocity is positive, but acceleration is negative. It must be slowing me down. That's all I know from that. Okay, that's coming from this scenario here. So write down your notes. How about the next parts? How could you have constant velocity? When is that possible? When is it physically possible to have a constant velocity?
There's no change in speed.
When there's no change in velocity. When there's no change in velocity, you can't have what? Acceleration in general. So acceleration has to be zero. This could be positive or negative. Ready? I could do this. I'm moving with a steady velocity or constant velocity. I'm not accelerating. That's positive. Or I can do the same thing negatively. It doesn't change at all. All that matters is to have a constant velocity. Acceleration must be zero. Must be zero. You will see this again when we get to Newton's laws with forces. F equals ma. Acceleration is zero when the object moves with a constant velocity. How about speeding up from rest? What do you got, Gabe?
Positive or negative for velocity or acceleration.
Okay, so the beginning, well, from rest, if it's from rest.
Yeah.
So I'm going to say from rest, it's got to be zero because I'm starting at zero. But what is this going to be?
Positive or negative.
Yeah. Okay, again, imagine, and this is, I'm saying from rest, that's why I'm specifying that. So I'm standing still, not moving. What's my velocity? So my VI, initial velocity, is zero, and then I'm going to speed up, either positive or negatively. It doesn't matter. But in order to move, you're technically always accelerating. So when you're standing there waiting for the light to switch to cross 83rd or Park, right? You literally are standing at zero velocity. You are doing this, exactly. Just to move, you have to accelerate. So that first step is acceleration. Because you're going from zero velocity to some velocity. So you're changing your velocity, so you must be accelerating. But what happens once you start crossing 83rd? What do? Usually you walk at a pretty steady pace, right? Most people don't do this. They're like, and then they're going to start running again. It wouldn't make any sense, right? It's not common sense. What would you do though? When would you accelerate? When you're at rest first. You're staying still, and then you start moving. That's your acceleration. That's what this last category is. How about remaining at rest? That's the easiest. To remain at rest. 0, 0. Very good. Okay, and that just makes sense. Think about it. How could you only way you can remain at rest is have no velocity and no acceleration. And you would remain at rest. Okay? So what we're going to do next, on the next slide, is just go through some new equations. We have some new equations that we're going to use. They involve initial velocity, final velocity, time, acceleration, displacement, kind of all the stuff we've been talking about. So this is where we're going to start, where you're going to have now, at this point you have 2 formulas. I'm about to introduce 3 more. So at this point now we're going to have 5 formulas under our belt. 5 formulas out of that whole formula sheet I gave you already on Moodle, the first 5. Okay, so that's what we're going to have to know at this point. So we're going to go over those in the next slide. I'm going to show you some of them, like where they come from, but the other ones I'm not going to go into too much detail. If you want to see what's called the derivation or where formulas come from, how they come about, your text does a pretty decent job of that showing that. Okay, so if you want to read through that portion, you can. It would be useful if you find that you like to understand that. But you're not going to have to show me where the formulas come from on a test. But you will have to be able to use those formulas. So if it helps you to understand them better, then by all means do that. Thank you. By all means, go ahead and take a look at the explanation. Okay, that works fine if you want to do that. Ernest, you had a question?
Yeah, so for this graph, is it basically like this one is speeding up for us because it starts at 0 and then it goes.
Speeding up, and then constant velocity, and then slowing down. Okay? All right, so our first, yeah.
Can you have velocity without acceleration?
Absolutely. So that means if your acceleration is 0 and you have velocity, you're moving at a steady pace. Because when acceleration is 0, it means there's no change in velocity. That's by definition, acceleration is a change in velocity. So if acceleration is 0, there's no change in velocity, so you have a steady velocity. This is exactly it, what I'm doing now. I'm at a steady velocity with no acceleration. But the minute I go to stop, I'm decelerating. Okay, again, think of acceleration as the change in velocity. What causes velocity to change? The accelerator in the car. All right, first formula, to show you where it comes from, very simple. It's actually the same formula as the one we just did. Let's write this down first. Let's write this down first, please. This is our formula we learned last week on Friday. Now, if I simply replace delta V with its definition, what does delta mean again? Change. So what should I replace it with?
No changes initial minus change final.
So it's, be careful, it's final minus initial. Okay, always final minus initial, please, this year. Final minus initial. So this formula that we've seen, and this is a formula that's very useful. How do I get rid of t if I don't want t in the bottom there? And I'm not saying I want a in the bottom, I just don't want t in the denominator. Multiply both sides by t. That's gone, that's gone. I'm left with AT over here, and VF minus VI. And the way this formula is traditionally written, and I'll explain why it's written this way, is by adding the VI over here. And this is how it's written. I'll explain in a moment why it's written this way. Okay, how do I get this? I add VI, add VI. This is why in your summer math packet, I pushed you guys to have to solve equations with only variables and with no numbers. You're doing it right here to show this. But what's boxed in is really what's important down here. So although this is the same arrangement as the initial formula at the top, see this formula we started with here? This is really the same formula. But sometimes it's useful when you want to find final velocity to just go right to this formula. And this is one of the few that is written on your formula sheet, even though it's written here already. It's kind of it's the same interpretation. You're just rearranging the formula here. Why might this be useful? Why might this be useful? Look at the form it's written in. It's analogous to something you've seen before. What is this analogous to? And it's not obvious because I've written it in a different way on purpose. I haven't written it in the exact same way you know it. I'll give you a hint. Okay, it's analogous if I put a y here and an x here. What else should go in those places?
But isn't it like the same as average velocity? The average velocity?
It's not the same as average velocity. Something outside of physics. Outside of physics. What does it look like? What kind of form? What kind of form is it written in?
So y goes on equal
Yeah, that's exactly what it is. This is the B and this is the M. It's not obvious, but it's there. Look at it now, seriously. Here's y. X is time. Isn't time always on the axis? So this is like your y-intercept. Isn't the y-intercept in math called the starting point? Have you ever heard that before? The y-intercept in math is called the starting point, starting velocity. What did we talk about earlier? What's the slope of a velocity graph? Isn't it just acceleration? Hey, take a look. Slope, isn't that what m is? Slope, acceleration. So if I wanted to graph this function here, if I were to graph my velocity versus time like we did earlier, this is vi. Let's say that it went up. Here's vi. And the slope is equal to the acceleration of the object. And here at the end is vf. That's what this is looking like, really. Okay, I don't have to put m equals a because you guys know I'm talking about slope here. But again, do this. We got this here. Didn't mean to erase it all. Okay, and again, the slope is acceleration. Slope is acceleration. So this formula looks just like y equals mx plus b. Looks just like point slope form. Let's see. Slope y-intercept form, sorry. That's all I want to say about that, because we're going to come back to this in a little while, but I don't want to jump the gun. I'd rather go into the other two equations first. All right, so again, that's equation number 1, the new equations from today. That's the first one. The next two I'm just going to give you now. All right, I'm not going to go over where they come from. This one is useful to show where they come from and how it correlates to a graph, so I do that. But the next two I'm just going to give you their formulas. Now, your text I mentioned again does show where they come from, but sometimes the text deviates a little bit from what I write in my notes. They're both correct, just different interpretations. So this is going to be x equals VIT plus 1/2 AT squared. That's the second formula we're going to look at. What does x stand for again? What does x stand for in physics? In physics, what does it stand for? Displacement. So the displacement of an object is equivalent to its velocity times time plus all this other stuff. Well, look, if you look carefully, it's difficult to see this, but look at only this portion, please. Cover up the 1/2 AT squared. In your mind, cover this up, the 1/2 AT squared. You're left with x equals v times t. That comes from the first formula of the year. Think back to the first formula of the year. I'm going to put a little side note in red on the right. Remember this formula earlier in the year? If you were to rearrange this formula and solve for x, what would you get to solve for x in this formula? What would you get? What would you get to solve for x in this formula? How do you get rid of t?
Well, you multiply to both sides.
So is that what you would get?
Yeah.
Well, look, this portion right here is the beginning of this formula, actually. That's all it is. Make the connection, please. Too many of you are either doing something else or just looking down for some reason. You shouldn't really be looking down at this point. Maybe write something, but I'm not writing too much. These are the same pieces. What's circled and what's boxed are the same thing. Well, in the first chapter, did we deal with acceleration at all? No, it was always constant velocity, average velocity. There was no acceleration in the first section, the whole first test of the year. So this equation in red on the far right over here simply involves no acceleration. Well, that's what this portion of it is. Where's the acceleration in this equation? It's over here. This is the acceleration piece of it. So this beginning portion of this formula really comes from this. But this formula involves acceleration also. So we need to consider the fact that the entire thing is important. Okay, the entire thing is important. This beginning piece is the same as this. This is where acceleration is useful. So that's the second formula, but it does relate to one of the old ones. And the third formula doesn't relate at all. It does not, but it's a result of combining these two formulas together. If you solve for one in terms of the other and combine and do what I had you do in that summer packet, where you solve for x and plug it into the other equation, or solve for vi and plug it in there, you end up getting this formula. Vf squared equals vi squared plus 2ax. And that's our third formula. Again, you know all the variables. Vf is final velocity. Vi is initial velocity. A is acceleration. X is displacement. So these formulas are 3 new formulas that we have to utilize. Let me give you or ask you a quick question. Let's say, hypothetically, I didn't know anything. I knew nothing about the displacement, which formula would I choose to use? If I knew nothing about displacement, I can't use displacement, I'm not looking for it, displacement is not involved. What formula, Jana, would I use? The first one. Why?
Because displacement isn't involved to from.
Exactly. There's no x in that formula. There's no x there. What formula is the one that I would use if nothing involved time? If I didn't have the time and the problem didn't ask me for the time. Neither of those things. Lauren? The third one, because there's no t in the formula. And finally, when would I use the second one most likely? If I had no knowledge of what? What's the variable that's not in the second one that's in the first and the third one? What's not in the second, Deirdre? VF. If you don't have the final velocity in the problem and you're not looking for final velocity, there's a good chance you're going to use formula number 2. So in this section, we're going to get to math problems in a second. We'll do one of them today. And then I'll have 2 more that we'll go over. But you need to pick and choose which formula you're going to use in the right time. Okay? In the right, whatever, in the right instance. I don't use time. A race car reaches a speed of 42 meters per second. This is where you have to never break up the problem. It reaches the speed of 42. What speed does it start at then if it reaches the speed of 42? Maybe 0. Probably 0 at some point. We don't know yet, but there's a good chance it was 0, right? So you might think, listen guys, focus. You might think that the beginning of the problem is 0 and the end is 42. By the first sentence alone, that's what you might think. Start off with 0 and end with 42. But that's not what happens because you got to keep reading. It then begins to have a negative acceleration. So I'm moving this way. Negative acceleration pushes against me. So what am I going to do then? Am I going to speed up or slow down? Slow down. I'm moving positive and suddenly negative acceleration. I'm slowing down. So the beginning of this problem turns out to be 42. It reaches a speed of 42, but then it starts to have negative acceleration using a parachute and braking system. It comes to rest after about 5.5 seconds. Determine the distance traveled during braking. Determine the distance traveled. In this problem, does it say that I'm turning? So distance traveled is the same as mine? Think back to your first test. Distance could be the same as another thing. Yes, when you're moving in a straight line. Good. Look, I take 7 steps this way, or 5 steps. I move 5 meters. My displacement and my distance are both 5 meters. The minute I start curving, isn't that where it varies? So there's nothing about turning in this problem. So right away, I can figure out that I'm trying to find my displacement. I'm really finding distance, but it turns out that the distance is equal to displacement in this problem. Now, I'm given the fact that there's negative acceleration. Do I know the acceleration? No, I don't know what it is. So that's still unknown. I know the time is 5.5 seconds. Now, again, be careful. We start at some speed, get up to 42. Then the problem begins. So 42 is what? The initial velocity. Again, get up to 42, then the problem begins, you begin to brake. So initial velocity is 42 meters per second. And I can again demonstrate it if you need to. You're going slow, you get up to 42 meters per second, and then you release the parachute, and you start slowing down until what happens? Come to rest, stop, which is 0. So this problem it doesn't matter that the car reaches 42. It could say a car is moving at 42 and then it starts to go to rest. What matters is that you guys recognize that, again, it's really starting at 42 and coming to rest. I don't care about it getting up to 42. That part of the problem is not of interest to us. That happened beforehand. We don't care about it afterward. The problem right now is that we're trying to find x. And the only formulas we have for x are these. Problem here is, I don't know acceleration or x. I don't know acceleration or x, and they're both here. So I can't use this formula. 2 variables are missing, and there's only 1 equation. It's not possible.
Or can you use equation 1 times a, and then plug it into it?
Very good, Ryan. So what Ryan thought of was saying, you know what, let's find acceleration first, and then we'll plug it into x. So here's what I want you to do tonight. Using this equation, using this one, solve for acceleration. Then once you have acceleration, you can actually even just use this formula. It's even easier. Okay, I'm giving you a little stepping stone, but I want you to do it. So use this equation to find acceleration. Once you know that, plug everything in here and you can find displacement. Turns out we don't even need this formula. Okay? We don't even need the one on the top right. There are 2 more problems. We will do them to start the double period before we do that next lab. Okay? You don't have to do this homework right now, but if you want to get a head start, I highly, highly recommend it. Because you will have a lab due later this week, and you're going to be inundated with a lot of homework. So I recommend starting this homework tonight, or the next 2 days. I don't see you guys tomorrow. It's not due yet, but I recommend starting it. Highly recommend it.
I know this one.
Yeah, so the same 5.5 goes here and here. 5.5. Square 5.5. Only 5. Then you multiply by A, then you multiply by B. The square is only on the T. That make sense? Seen it break out? Seen it break out?
Would you mind just to send me one too?
Sure.
Just because I'm going to find his errands. Like,
Got a scenario here where a plane starts at rest. It wants to undergo, or it undergoes uniform acceleration in order to lift off. It takes about 15 seconds before it actually lifts off. The question is, what speed is it necessary at takeoff, and how long must the runway be? What is the speed necessary, and how long must the runway be? So, these values are actual values that would be used for an actual airliner. They accelerated around 5 meters per second squared, the acceleration that they had. And here, 4.8. I'm trying to think, last time I took off, how long do you think it takes actually? From when they actually say, okay, prepare for liftoff, and they start going. It's probably 15, 20 seconds, right when you lift off the ground, I mean, that exact moment. Maybe 15 or 20 seconds for that to happen. Why might this be an important problem? Why might this be an important problem? And think outside of obviously just airports, because obviously the plane needs to know where it's going to lift off, the track and stuff. Why might be a more important problem? Think of another application that would involve lifting off for some sort of object that might have some constraints involved. Might have some other characteristics they have to develop.
It's not precise when you have a problem.
Alright, that's a good answer. Yeah, there are other planes in the air, so you have to follow the trajectory that's set. So you want to lift off at the correct time, so you're not off on your track. You have to compensate for that along the way. Planes do compensate for that. They have a feedback system and that keeps them on the course the entire time.
Where do you keep the disk? I don't install it. I can find
It's on my desk.
Okay.
Right on my desk. You'll see. Where else might this be necessary? Think about a military application. Think about a military application.
Is it on a carrier?
Yeah.
And they shoot off from the...
Exactly. On an aircraft carrier. Aircraft carriers only have a certain amount of distance on the actual ship. The ship can't be as long as you want it to be like a runway can, right? So you need to know the actual length necessary for takeoff. Well, that's the length of the ship, or the runway of the ship, that has to be at a minimum before this will take off. If it doesn't make it in time, obviously, it goes off the end of the actual carrier. So you might need to figure out the actual length that's necessary. So let's go ahead and list our givens first. What do we know? What do we know?
Acceleration.
Which is?
4.8 meters per second squared.
Good. 4.8 meters per second squared. Obviously, we also know the time. Time is what? Anybody? 15 seconds. What else? I know one other piece. Lauren.
is that the thing was at rest? And then
It started at rest, so give me a variable, Lauren. It's at rest. What about it? Do you know? It has no. What term? If it's at rest, it has no velocity. So what could you say if it has no velocity? What could you say if it has no velocity?
0.
Yeah, what about which velocity? Which one? Initial, right? VI. Because again, it starts from rest. It starts from rest. All right? So this is how we break down a problem in physics. This is how you have to do it every single time. When I told you about this format, and I said it's a very high suggestion of mine, It's almost a requirement for some of you right now because on that second part of the test, I didn't see a lot of this. I didn't see a lot of this because there was one problem that you could have definitely done this setup, this arrangement, list the givens, list what you're looking for, list the formula. You could have done it with the problem where you're calculating the time it took, forget whose name I used or what student it was, to climb over rocks or to boulder at one point. Who was it under? Maryland. Okay. And Maryland was an outdoorsy person that day. But the time necessary for that, you needed the time for part A and the time for part B, and then you have to sum those together. But it's the same approach. You should have listed the velocity given, the displacement that was given. You should have wrote time equals question mark. Same exact approach. So when you see your next homework assignment, which you're going to have, that's going to be due tomorrow for you guys, from this section, and you're working on this, you want to take this approach for every math problem. Okay? And if you don't know if it's a math problem, you need to look at the problem and say to yourself, am I given enough variables to make it a math problem? That's how you can tell physically. In this problem, if I were going through this and I were saying to myself, all right, you know what? Let me highlight what's important. I'd be highlighting this. I'd see this. And I'd see this. Okay, that's the first three things I would highlight. And I would say those are my givens right there. And then I'd say, okay, what am I looking for? Speed at takeoff. And what else? How long must the runway be? That's what I'm looking for right there. So those are the pieces of information that tell me right away that this is a math problem because I've got enough variables and I'm looking for other variables. So when we list the other variables, we can then take those and utilize those to pick the formula we're going to use to solve. It's a strategic, regimented approach every time. You take the same structured approach every time you go through one of these problems. And throughout the year, you're going to do math problems for every section. There's going to be some math application to every topic we do. So what is the speed at takeoff? What are they asking us for? Speed at takeoff. What would that be? It's not necessarily obvious this time. Speed at takeoff. What would that be? Yeah, the final, let's say, for this case, exit final, the final velocity involved. Oops. Okay, the final velocity. Now, if you didn't know that off the top of your head, let me draw a diagram real quick. And you're going to see my artistic skills just come into play. Like crazy here. Not really, though. That's not bad, right? All right, there we go. So here's our plane. It's on the runway. Suddenly, it turns its turbines on. The turbine starts spinning, pushing it forward, propelling it forward. Newton's second law, equal and opposite reactions. It starts to move, and then at some point, it takes off. This is initial, and this is final. That's what I'm talking about by breaking the problem into pieces. Does this problem incorporate what the plane is doing once it's up in the air? Does it ask about that? Does it ask about how long it flies for? Its velocity while it's coasting at 3,000 miles? Or 30,000, whatever it is. It doesn't ask about any of that. Not 3,000 miles, 3,000 feet. It doesn't ask about any of that in this problem. So there's initial and there's final. So since we're looking for the speed at takeoff, it's sometimes a little bit confusing because students see the word speed. And yet I wrote VF. Again, it asked for speed, yet I wrote VF. How is that allowed? Why can I call speed final velocity in this problem? How come speed at takeoff is the same as final velocity? Lauren.
Did you say like yesterday with the tape, like when the tape like hits the ground or if the tape ends up with it, it's like the same as for final velocity, so it can be the same thing here, like when there's tape off like in the air, it's the same thing.
Yeah, so it's the very end of the problem, but I mean specifically, why are the words speed and final velocity interchangeable in this problem? For example, the problem says, what is the speed? Why am I not solving for the term speed? Why am I allowed to say, what is VF?
Well, there's a difference in direction, right? You're just going from one place to another. It would be the same displacement as distance.
So if you think about this, the plane is only going in one direction. The plane is traveling this way. So if I know what the actual speed is of the plane at this point when it's lifting off, the velocity is the same because it's still only going in that direction. Remember, if you're traveling in a straight line, you can interchange the words displacement and distance. You could also interchange the words velocity and speed. Velocity really indicates a direction. Do I care if it's going positive or negative here? No. Because if I'm on an aircraft carrier, like we were talking about earlier, that boat might be oriented in any direction. Actually, what does that boat do? That boat's able to pivot, actually, so that the takeoff could think about it. You might want to take off at a different angle. Now, I'm sure the boat can orient itself in any direction and then anchor down. I'm sure also planes can take off in one direction and then start to turn. But depending upon the application of it, it may not want to turn. So the boat itself may change its orientation. But the concept here is that, yeah, I'm traveling that way, or I'm traveling that way, or I'm traveling that way, or that way, but I'm traveling in a straight line. So speed and velocity are really the same thing when I'm traveling in a straight line. And it's difficult to kind of get through that point, because I'm not caring about negative or positive in this case. So when it says determine the speed of takeoff, that's actually the velocity at the end of this problem. This is the end of the problem right here. Right as it takes off, that's the end of the problem. You're going to hear later in this year, we're going to drop objects. This is going to be the beginning. The end of the problem is going to be the instant before it hits the ground. Not when it hits the ground, but the instant before it hits the ground. Because we're going to determine what's called impact velocity. And yeah, when it hits the ground, what happens eventually? Stops. So I would get some smart-ass answers in other students last year. Oh, it's zero, the final velocity. It stops. That's not the final velocity, obviously. The impact velocity is the velocity the instant before impact. That's what you would have for impact velocity for any vehicle that's moving. Impact velocity, the velocity the instant before impact.
I tried uninstalling it, I tried repairing it, I tried troubleshooting it. I think if there's one thing we just want to read this. So that's the only thing I can find.
Just see if he can activate it for you. He might be able to do it. Thanks, Ed. All right, so the second part is how long must the runway be? Again, I'm traveling in a straight line, right? So this is my direction of the plane motion. It's not turning or anything like that. It's a straight line. So the length of the runway could be either distance or displacement in this problem. It doesn't really matter. Because, again, I'm using my physics formulas here, I'm going to use displacement. I'm going to say I'm determining the length of the runway, the displacement the plane undergoes before takeoff. Again, this is x. I'll draw on the diagram. Here's x. Okay, that's what x is, that dimension right there. Okay, the distance or displacement the plane undergoes right before liftoff. Okay, it doesn't matter in this problem if you use distance or displacement really, because it's only a plane moving in one direction. So for this problem, what do we go for first? What do you recommend? I can now slide up. I don't even need the problem. Take a look, by the way. Did you notice that? Watch. Ready? You don't need any of these words. And now you can still solve this problem. That's what doing this does for you. Look at the arrangement you have in front of you. You're given three things. You're looking for two. So as a result, now you just got to pick your formulas. Go back, please. Everybody do this. I'm going to give everybody a minute to do it because you need to practice this. Go back to the formulas 1, 2, and 3 from yesterday or the day before with you guys. Okay, formulas 1, 2, and 3. The three new formulas from this section. Which of those formulas am I going to choose to solve for these two missing variables? Come up with both formulas, please. I'm going to give a minute so people can take a minute to write them down. Practice on your own. Figure out which formulas you're going to use to get VF. Figure out which formula you're going to use to get X. And when you tell me, I want the order in which you're doing them, please, too. So which one are you solving for first? And it doesn't matter. You could solve for either of them first, actually. Both ways work, but you end up taking different formulas if you take a different approach. George, give me one of the approaches you would take.
Well, you could use Formula 2, then Formula 1.
Can you read the formula first?
Yeah.
Formula 2, which one is that? They're not known by 1, 2, and 3, by the way. I just put numbers 1, 2, and 3 yesterday. So when you reference the formulas, give me the formula. Go ahead.
Initial velocity times time plus 1/2, acceleration times squared.
So what's the formula though solving for, George?
X.
Thank you. So x equals
Uh,
VIT.
Yeah, plus 1/2 AT squared.
There you go. That's how I want you to read it. So George is absolutely right. We could start by finding displacement. We have acceleration, we have time, we have initial velocity. It's convenient, this problem. What's initial velocity? What is it? So what happens to that whole term, VIT? It's 0, because 0 times anything is 0. 0 times 15 is going to be 0. So you could write this. That's how I represent that a term goes to 0. See that? You're going to see this in your math courses if you take at least pre-calc and calculus. This means this term goes to 0, meaning it's 0, drops off. Okay? Because what was the initial velocity? VI was 0. It's just going to be 0 times 15, which is really just 0. You don't have to show the work there. Drop it right off, okay? If you solved with this approach and you got x, how would you then get VF?
VI plus AT.
Yeah, I would use this approach. There is another formula. I would agree completely. And again, VI would drop off. That would go to 0. So you get VF by just doing A times T. You have A, you have T. VF is done, really. This problem's easy to find VF, right? You could have also used VF squared equals VI squared plus 2AX, because now you would have had X, okay? Now you would have X. That's the other approach I was going to show. But I really probably wouldn't even take that other approach. It doesn't make sense to take a square root, right? Like the other approach would be the same thing, really. You would use VF squared equals VI squared plus 2AX. Once you know X, you could use that X here and solve for VF. But I would not want to take a square root in a problem when it's not really necessary. In the first setup, I don't need to take a square root to get VF, so I would just solve for it. Okay, so go ahead, find X and find VF. Get your numbers, please. I'll check your numbers in about 30 seconds. Use your calculators, please. Get them out. Use them. I'm going to start marking you off unprepared if you don't have a calculator. I will start soon if it doesn't change. I had to do it last year. People were losing points every day. Get a calculator. All right, so let's do this.
I think I can boil up the meter doesn't show up as an option.
A faculty does work up,
Yeah, faculty works.
and it's already logged in.
Yeah.
Can you grab a different device? Did you try that already?
Yeah.
Yeah, because last year I noticed that a couple devices weren't working, and I think the second day when me and Caroline did it, I think we used a different device. So maybe it's the same device that's not working. Let's check real quick, see. Yes. What's the what? What do you think? Yeah, because what does X measure? Length, distance, length. Good. And are you still getting that same error that we were getting a moment ago? And did you Google this by any chance? Sucks. Sucks so much. Yeah. I don't think there are any in the room. You could use the paper towels, or you want to use the bathroom. I don't have it. So give you one. Sorry about that. What do you get for X? What do you get for X? X. Brian. Or VF, either one.
Oh, yeah.
Sure, whichever. VF is 72, agreed? Units?
Yes.
Units? Velocity, units. It's not miles per hour, it's meters per second. When you forget what velocity units are, think about driving a car. Miles per hour, but we don't use miles and hours. We use meters and seconds. So go back to meters per second. Who's got, somebody go to Google and convert 60 miles per hour to meters per second, please. Go ahead and convert 60 miles per hour. So type in 60 mph to meters per second. Just write the word 2 and then m/s. It's meters per second, just to give us an idea of what 60 miles per hour is. And the displacement, what was the displacement? What was the displacement in this problem? Ernest? Agreed? Others? Yes? I agree as well. Okay? Yeah, question? I'll get it, yeah.
26.822.
Oh, okay. That's what she was, I thought you had a question.
Yeah, I do have a question.
Answer the question, yeah.
For
Yes.
the final velocity,
Which, I don't remember. Did we do that for you?
This one here?
Yeah.
Yeah, but you had it written backwards, I think. I think you had VF, you had VI plus AT equals VF, I think, on your notes, right? It was the first of the three formulas, Ernest. It was the one that we solved for. We did all the work for it.
Oh.
Okay.
Computer says disconnected for faculty and needs the password for this one.
So for computer, can you put the password in? Does it allow you to?
It should work. I don't know what's wrong with it.
Go over to network. Open. Go to forget. You forget network now.
Oh, sorry.
Cancel. Hit off and then back on. So it turns out that 60 miles per hour, Caroline, what'd you say it was? Is what? 28.6 meters per second, approximately. So that's a great idea to think about this, guys, all year. All year long. What's your rule of thumb you can now say? Approximately. It's an approximation. When converting your answer from meters per second, you want to get an idea of what it is in miles per hour. What should you do? Approximately. Multiply it by 2. Go from here, again, either direction, obviously. Don't say add 30. It's not the rule, because if I have a speed of like 10 meters per second, I can't just add 30, I have to just double it. So it's approximately double.
It's actually 26.8.
Sorry, 26.8. Still though, around double. Let's just, again, guys, we're not, yes, if you are a research scientist one day or an engineer, you need precision in everything you do. Because if not, people die when you build stuff. Seriously. You really do. You need precision in all things you do if you study engineering, if you go into real science in college. For the sake of physics, I want you to have an understanding of numbers, right? So I'm going to say to you, it's about double. Just like I happen to know, if I'm trying to convert between kilograms and pounds, I know that a kilogram is around 2.2 pounds. I just happen to know that number, and I keep it in the back of my head. So whenever we do problems with masses, I can get an idea of what that feels like. If I'm like, all right, we have a 10 kilogram mass, in my mind, I'm like, that's 22 pounds. Okay, that's about the size of like a weight in the gym, 22 pounds. Think about how many things. So keep an idea of how you're going to go through this, and approximately double. Okay, try the last on your own, please.
Should I try the?
Try the last one on your own, or with the person next to you. You can do either way. Yeah.
So I forgot the number, but now it's going to show me again.
Okay, so now there's a way to add them, actually. And I think that's what I ended up doing. Because Richworth kills me. He makes, for some reason, the logo of the computer network unviewable. I don't know why it is. He told me about it like last year. To create a network. So let's create a network and use the exact same credentials I have here for the computer. It's really normal. Alright, so those will be all cash. Actually, I just changed Check your answer with the person next to you, please, when you get it. List your givens, list your desired, list your formulas. If you're really struggling, maybe ask somebody next to you for help for a second. I'll come over in 2 seconds. And now that we got this one, it's not asking you to log in. No.
I think you chose to start with right instead of doing one. I think I just made it network and so
Alright, so if that doesn't work, go to join and try. Run through that installation first. Sorry, Ann.
Oh, this.
Take a look up. Take a look up.
Which makes sense because it's their time.
So it looks to me like you have three things that were given in this problem, and you're looking for one thing. A person pushes a stroller from a velocity of 3, uniformly accelerating it. What is the velocity of it after it's traveled 4.75 meters? So give me what we've got here. What's VI? Ernest?
3 meters per second.
Yep. Again, from a velocity of 3, meaning starting at 3 meters per second. Guys, you need to know your units. You need to know them so well, because when you see this, you should think velocity automatically. Whether it's final or initial, 3 meters per second is a velocity. The units are so darn important, I can't even, I want to yell it right now. I'm not kidding. Okay? Put it on your formula sheet. Put it next to your variables. It's so important. Meters per second squared. What does that make you think right away? Meters per second squared. What is that automatically? Automatically. Just from the units alone, Amaya? Acceleration. Obviously it says the word accelerating. I get that piece. So that was probably your key. But from the units alone, you would know that this is acceleration. And finally, why did I put x? How do I know you're given x? Right? Meters. Good. It traveled 4.75 meters. Nick?
For the distance, do you have to write delta x?
No, again, remember, in these problems, in the formula you used a moment ago, x equals VIT plus 1 FAT squared, that x was solving for the overall displacement. So we're still looking at displacement here. If you want to use the term delta, you can. And you just assume that the person started from 0. You're just, you know what I mean? From 0 to 4.75. Maybe the person started here and walked 3 feet. Maybe they started here and walked 3 feet. But either way, x would be 3 feet or delta x would be 3 feet. I don't know the final and initial. If a problem gives you the final position and an initial position, subtract them to give yourself x. So inherently, Nick, this is delta x, but it's not written that way. So if we're looking for VF, what formula would you recommend we use? What formula should we use, Amaya?
I use VF squared equals VI squared plus 2AF.
I would agree. What is not known in this problem? What is not known, Gabe?
VF.
VF is what we're looking for. But what's not known as far as like at all? You want to follow? T, good. T is not known and you're not looking for it. So I should say what is not involved, I should have said, right? What is not involved? T. What is not known? Yeah, Gabe, you were right. VF is not known. That's what's not known. So let's go ahead and solve for VF. Well, all you got to do here is plug in. This is probably the easiest solution of the year because VF is on the left-hand side. So plug in and then take a square root. Right? Plug in and take a square root. So all you do is plug in. You're going to get some number on this side. VI goes here. You square 3. Your A goes here. You put it in there. Your 4.75 goes over here at the end. So you get some number. Get rid of the square by taking the square root. This is why that summer packet was I was talking about being able to solve this. You need to be able to solve this a little bit quickly. Okay, if you struggle with what I was just saying, then let me write it out real quick because I'm not seeing the most clear looks on faces. So VI squared plus 2 times A times X. And then how do you get rid of the squared? You take the square root of both sides. So that would be your final answer. Okay, get rid of the squared. Yeah?
Can we do it out in the calculator if we just leave it like square root of?
I would do it all out. I mean, in physics, you give a number usually with nearest tenth or a decimal point. Usually you don't answer with a radical in physics because a radical Doesn't have any real significance. You want to know what that actual value is, so an estimation is usually better. What do you got, Gabe, for your estimation?
2.17.
Is that correct or incorrect?
I got a 3.7. Yeah. Because you have to add it.
Check your work real quick. What did you get?
I got 3.71 meters per second. Well, we had 3.7.
3.71?
Yeah.
3.7? Is that better?
Yeah.
Just so we all agree?
Or is it 10? No,
Yeah, I usually just say the 10th, honestly. I don't really give a hard time about this, unless the number is like really small. That's not correct, so check your work. It's definitely 3.7. Now, what should I apply to this answer? I took a square root. When you take a square root, what should you put in front of the answer? Plus or minus. The reasoning is this. A velocity, the velocity could be positive or negative. Remember? The direction matters. You need to use the context of the problem to know what's happening here, though. So was this velocity initially positive or negative to start? Was the velocity positive or negative to start? Positive. The initial velocity was 3. Was the acceleration positive? Was the acceleration positive? If the velocity is positive and the acceleration positive, the object is doing what? From yesterday's class or 2 days ago. We made that table. Velocity is positive, acceleration is positive. What are we doing? We're speeding up. So as a result, if you start with 3, you have to get to something greater than 3. It can't be less than 3. So if you get an answer that's like 1.5 or something smaller, it's not reasonable as an answer. Does that make sense? Secondly, the negative you don't have to worry about, because clearly for this number to be greater than 3, it's not going to become negative. It's going to remain positive, and it's just going to get simply larger. So for the context of this problem, this would be your answer. Because we know the answer is positive. We don't need the positive or negative, but I'm saying how you understand it conceptually as opposed to mathematically. Mathematically, yes, the answer is plus or minus. But realistically, it's just the positive.
Yeah, that all works.
George, question.
Would you solve this problem by solving for x? Like b equals 1
X is given.
Should I hand back the
So
line?
there's no final velocity. Final velocity is and isn't that when you?
No, X is given. You said would you solve this by solving for X? X is right here, 4.75.
Okay.
See what I'm saying? There is another way to do it. You could have used VF equals VI plus AT and this and another equation combined, but it's not going to make sense. It's a roundabout approach. Yes, I agree. Before you get up, Anthony's going to give you back some old homeworks and your last labs. Maya, before you... Oh, sorry. Names. Sorry. Yeah, you're nice. Come on.
No, I'm not.
Maya, before you leave. That's fine. Please, I don't know everybody's name yet. We're going to do this.
I know, I wasn't trying to be mean.
All right.
I just thought it was funny.
It was funny, but
So mean.
so the other class is going to do the first period tomorrow. Is that what you're saying?
Yes.
Okay, so working out well. Okay, so see you then. Tomorrow the homework from this section is due. Okay?